Okay. Okay, so if we multiply 2, -3, -4, 6 by AB, we get this. Okay? So if AB is a vector, it goes over here someplace. So your 2A minus 3B negative 4A plus 6B is over here. Okay? If we row reduce this vector, or this matrix, this is what happens. Okay? Because 4 times 1 is 4, and 4 minus 4 is 0. 4 times -3 halves is -6, and 6 is 0, right? Okay? What can you tell me about this vector?
They're parallel. See, 2 zeros.
Well, first of all, since the matrix reduces down to that, what's that tell you about these 2 rows? Well, huh?
Oh, so someone asked on the same line.
They're on the same line. Why would they be on the same line?
Well, as far as being dependent when reducing a system of equations,
Why are they dependent?
if when it reduces to 0.
You're going in a circle and you're not quite back to the basics. But yes, everything you say is true, but you haven't proven it because, okay, so. Oh, I did have the camera on. So, what you said is good, okay? I was going to go back over all that, the camera's been on. Okay, so, well, if you this stands for 2A minus 3B, right? This stands for minus 4A plus 6B. Okay? If I divide this by 2 and then add 4 times this to this, I get 0, right? So one row is a multiple of the other. Okay? If we take half of the first row, multiply that by 4, add row 2, we get 0. Okay? Well, 4 times half of row 1 is 2 times row 1. Plus row 2 gives us 0. So row 2 is negative 1/2 times row 1. Okay? So what we get here is two a minus 3b times 1 negative 2. Okay? Which means that any vector over here transforms to a multiple of 1 negative 2. Okay? Now the vector 1 negative 2 is here. Any vector over here has to go to a multiple of this vector. Okay? That makes sense? Do we understand that argument? First of all, you just observe that whatever a, b are, what you get over here is 2a minus 3b times 1 negative 2. Okay? And the evidence for that is in the reduced matrix. The matrix reduces down to a matrix with a row of zeros, which means anytime that happens, you can do this. Okay? Keep track of what you're doing, because, you know, this is right, and then this is two plus 4 times 1, and the one that this is 2 plus 4 times is this one, which is half of the original one, and you conclude then that this row is negative 1/2, or a negative 2 times this, or negative 1/2. Uh-oh, maybe I did that wrong.
Is it negative 2?
Yeah, it's negative 2. In careless, I know of a vaccine against that, so we're kind of stuck with me being careless, but watch me. Okay? So, make sense? Anytime this thing reduces to 0, 0, you can write out this and figure out what multiple the second row is of the first, or the first of the second, depending how you want to do it. Okay? Then, A and B are arbitrary, so 2a minus 3b can equal any real number. So the range of this transformation consists of all real number multiples of 1 negative 2. Well, where do all the real number multiples of 1, negative 2 land? If you start the vector at the origin, where will all the multiples of 1, negative 2 be? Along that straight line that's defined by this vector. Okay? All real multiples of 1, negative 2 and on this straight line. It's nice and straight the way I drew it. Okay? I'm looking at it from a bad angle. My shoulder's a little stiff today. And I'm not that great at drawing straight lines anyway. So that's the main thing. So it didn't come out that straight, but you understand where it is. Okay? Okay, so what we notice is the matrix has one row of zeros. It reduces to say the reduced matrix has one row of zeros. Okay? So one row is a multiple of the other. So the transformation collapses R2. Now I haven't used that notation before. This just means real line by real line. Real numbers by real numbers. If it was R3, it'd be real numbers by real numbers by real numbers. If it was R4, you wouldn't be able to visualize it, but you could still depict it. I mean, you could still write it as a column of four numbers, right? You could write the typical vector. Each vector is a column of 4 numbers. So it collapses R2 to a one-dimensional subspace of R2. So this straight line, it picks a one-dimensional subspace of R2. Okay? So every vector in this plane maps onto this. Okay? Plane collapses to a line, one-dimensional subspace. Now, if the transformation is defined by a matrix that has numbers in the spots where the asterisks are. Okay? Then what's the dimension of vectors in the domain? Well, what do the vectors in the domain look like?
Real numbers.
Huh? Well,
Real
they're not
numbers.
real numbers, no, but they've got real numbers in them. More specifically, what are they?
Identical?
Ah, nice try. Thanks for saying. Can you give me an example of a vector that this matrix could multiply?
X squared plus X plus 1.
Again?
X squared plus X plus 1, like a polynomial?
You can't multiply a row by polynomial. But you could represent the polynomial by the coefficients of x squared, x, and 1, and the constant, okay? So you could do that, okay? And we're actually going to do that, so it wasn't necessarily a bad idea.
Should I be scared?
No. You're not coming up with any ideas either. You're both smart as heck.
A column vector of 3?
Yeah, it's got to be a column with three. Yeah, it's got to be a three-dimensional column vector. Okay, well. Rows have three numbers. You got to multiply rows by columns. So the domain consists of column vectors of length 3. Right? Then I'll just depict that by, got to look like this. And in what space would you depict these column vectors? What space would you draw arrows?
3-dimensional space.
I'm sorry?
3-dimensional space.
Yeah, three-dimensional space. Okay? If it's a real space, then it's R3. Three-dimensional space, right? Okay? Okay, well, first place, when you multiply this matrix by a vector, what kind of a vector do you get? What's it look like?
3 and a
Yeah,
column.
you got, it's a column vector of 3 because you got 3 rows. You know, first row times a column is going to give you this number. Second row times a column is going to give you this number. Third row times a column is going to give you this number. Okay? Okay, now I'm saying, and I'll probably ask you to try to prove this, if the matrix reduces to this, then the range is all of R3. Okay? Now, more interesting, although that's interesting in itself, what if it reduces to this? Now remember, the domain is all the vectors you can multiply this by, which would be any vector, all vectors in R3, right? So domain is all of R3. The range is not necessarily all of R3, although the range is a subset of R3, actually subspace, okay? Just like in the first example, when we had all of R2 mapping onto a line that's a subset or subspace of R2. Now, I haven't defined what a subspace is, a fairly simple idea, but I'm going to use it anyway. And then maybe we'll talk about what a subspace is and give you the criteria for subspace and ask you to prove a couple of things. Okay? I still haven't looked at Mark handed in here. We'll see what kind of proofs I want to give you. But I think your basic idea of proof is going to be okay. Okay. So, if the matrix reduces to this, the range is all the vectors you can get. Now over there, you couldn't get a vector that wasn't on that line. Okay? What about here? Well, it's got to be part of R3 because any vector in the domain that gets multiplied by this matrix is going to give you a vector in R3, right? But from what we saw previously, we know it doesn't have to be all of R3. Okay? So what do you conjecture by analogy with what we just saw?
It look like a plane.
You could go that far. One thing you could conjecture is that it's not all of R3. Okay? Okay? And it's the range. That's implicit in what's right before it, just to be sure we don't lose track of that idea. The range is not all of R3. Okay? And slightly more dangerous conjecture. It's a plane in R3. Okay? What has to happen for the matrix to reduce this way?
One of them has to be parallel with the other.
Okay, well, yeah, your first row does represent a plane, and your second row represents a plane, and your third row represents a plane, right? Okay? And from what we looked at last time, it's very plausible these planes aren't independent. Okay? Doesn't necessarily mean that one's a multiple of the other. But it means that they intersect in a plane. Okay? So that if you add the equations for the two planes, you're still in the plane. Okay? In other words, in order for this to happen, one row has to be a sum of multiples of the other two. Okay? Now maybe that means two of them are the same plane. You can think about that. Okay? Okay? So I can say that to get okay? So you can worry about the geometry of that. But they can't all be multiples of each other. Because what would happen if they were all multiples of each other?
Zeros across the board.
Huh?
Zeros across the board.
Well, not on every row, but you know, your first row would still be what it is, but if you add the right multiple of that to the second row, it goes away. And if you add the right multiple of the first row to the third, it goes away, right? Okay? So it's not zeros across the board, but it's a lot of zeros. So good intuition. That would lead to this, right? And we're assuming that, well, you got a 1 here and a 1 here. These could both be zeros, but probably not. It could be any numbers, depending on their transformation. Okay? So you don't have two rows of zeros. If just one row is a sum of multiples of the other two. Okay? Now, technically, one of the rows could be 0 already. But if we're assuming that the stars are not zeros, okay, that would be the case. But they could be zeros, so you kind of have to worry about that a little bit. Don't let it give you nightmares just yet. Okay? So, good intuition. Okay, well, rows represent planes. So, reducing to this matrix implies that the original matrix maps R3 to a plane in R3. Okay? So, I can kind of depict that. Yeah, I'm gonna use a different word. I don't have space here. So, a plane in R3, okay? Now, one of the easiest ways to represent a plane in R3 is to show the points on the axes where that plane intersects. So if that plane intersects your three axes at these points, which is the case unless the plane happens to be through the origin, okay? You can kind of represent it by shading this much of the plane. Okay? But we make a convention that all vectors are represented with their initial point at the origin. So the plane does have to go through the origin. So I'm showing you a plane that isn't through the origin. So I'll just say except the plane is through the origin. Okay? And that's a little harder to depict. Okay, so I'm just going to say, okay, here's a plane. And maybe I'll shade that plane in a different color. And indicate that it goes through the origin. Now, we're not doing multivariable calculus, but you can